is called co-option.
It's essentially saying that evolution or natural selection at some point was able to borrow components of one molecular machine and build a new machine with some of these components.
Scott Minnick has studied the flagellar motor for nearly 20 years. His research has led him to challenge the co-option argument.
With a bacterial flagellum, you're talking about a machine that's got 40 structural parts. Yes, we find 10 of them are involved in another molecular machine, but the other 30 are unique. So where are you going to borrow them from? Eventually, you're going to have to account for the function of every single part as originally having some other purpose. So you can only follow that argument so far until you run into the problem of you're borrowing parts from nothing. But even if you concede that you have all the parts necessary to build one of these machines, that's only part of the problem. Maybe even more complex, I think more complex, is the assembly instructions. That is never addressed by opponents of the irreducible complexity argument.
Studies of the bacterial motor have indeed revealed an even deeper level of complexity. For its construction not only requires specific parts, but also a precise sequence of assembly.
You've got to make things at the right time. You've got to make the right number of components. You've got to assemble them in a sequential manner. You've got to be able to tell if you've assembled it properly so that you don't waste energy building a structure that's not going to be functional.
Building a molecular machine has been compared to the construction of a house, where workers follow a detailed blueprint and plan for assembly. The foundation of a house is poured before the walls are erected. Plumbing and electrical fixtures are installed prior to enclosing the walls of the structure. Windows must be hung before siding is applied, and shingles are attached only after plywood sheets are nailed to the rafters.